In this video, we shall be discussing traveling salesperson problem. The problem statement goes like this. In case of traveling salesperson problem, given n cities, a salesperson starts at a specific city, often called source, and visits all n-1 cities exactly once and returns to the city from where he has started. The objective here is to find the route through the cities with minimum cost. The cost of a tour is the sum of the cost of the edges on the tour. The traveling salesperson problem is to find a tour of minimum cost. A tour is a simple path that starts and ends at vertex 1. So, you are given a graph with a set of vertices and edges, which is a directed graph with each edge associated with a cost denoted as Cij. So Cij stands for a cost for an edge from I to j. Cij is greater than 0 for all ij, and we consider C of ij is equal to infinity if there is no edge from vertex I to j in the given graph. And we assume that the vertex set V has n number of vertices in it such that n is greater than 1. Every tour consists of an edge 1k for some k that belongs to vertex set V, excluding the vertex set vertex 1, that is the source vertex. That is, k belongs to a set of vertices that have all other vertices except for vertex 1, and a path from vertex k to vertex 1. So every tour consists of an edge 1 to k and a path from vertex k back to vertex 1. A path from vertex k to vertex 1 goes through each vertex in v minus 1 k exactly once. Let g of I, s be the length of a shortest path starting at vertex I and going through all the vertices in the set S and terminates at vertex set 1. From the principle of optimality, g of 1 vertex set excluding the source vertex 1 denoted as v minus 1 is equal to a minimum value obtained from C of 1k plus g of k v minus 1 minus k. This gives us the length of the optimal tour. The previous equation can be solved for g of 1 v minus 1 if we know the values of g of k v minus of 1 k for all choices of k. The g values can be obtained using the following equation, that is g of I, s, which is a minimum value from C of ij plus g of j, s minus j. And it's clearly noted that function g of I, null is equal to C of I1, where I ranges between 1 to n. Null means that it is C of I1 is the cost of an edge starting from vertex 1 to vertex I. Let us say function g of 1 comma v minus 1, let us denote it as equation 1, and the function g of I comma s denoted to be equation number 2. Hence, we use equation 2, that is g of I comma s, to obtain shortest path from vertex I to all other vertices in the set S. Initially, for all set S of size 1. Then for set S which has 2 vertices in it, and so on. When the size of the set S is less than n minus 1, the values of I and S for which g of I comma s is needed are such that I is not equal to 1, that is, I is not a source vertex, and 1 does not belong to the set S, that is, the source vertex 1 does not belong to set S, as set S has all other vertices that lie in the path, and I does not belong to S, that is, g of I comma s is finding path from I to vertices in S. Therefore, I cannot be in S, as self loops are not permitted. So now let us solve the traveling salesperson problem using the dynamic programming approach for the given graph. So if we observe here, we are given a graph and the edges of the graph are bidirectional edges. It means that you can read the edge from 1 to 2 as well as back from 2 to 1. So this matrix gives us a value of the cost of the edges. So I number it as 1, 2, 3, 4, and columns are also numbered as 1, 2, 3 and 4. So I read it as edge 1 to 2 has a cost 10, edge 1 to 3 has a cost 15, edge 1 to 4 has a cost 20. So similarly, edge 2 to 1 has a cost 5, right? And as I said, self loops are not permitted, so therefore the values in the diagonal are set to 0. That is, we do not have an edge from 1 to 1, edge from 2 to 2, 3 to 3 and 4 to 4. So in the first case, wherein the set S has no vertices in it, wherein the cardinality of set S is equal to 0, we make use of equation g of I comma null, which is equal to c of I1. So therefore, g of 2 null is equal to cost of an edge from 2 to 1. So 2 to 1 we have a value 5. Similarly, g of 3 null is cost of edge from 3 to 1. So from 3 to 1 we have an edge of with a cost 6, and g of 4 comma null is an edge coming from 4 to 1. So therefore its cost is 8. So the second case is when we have at least one vertex in the set S, right? And always the source vertex, that is 1, cannot be part of this set S. So initially we start from g of 2 comma 3. Set S now has a vertex 3 in it. So we start from 2. So the value of 2 is now nothing but I, and the value 3 is j. So this time we try to find out minimum of Cij, that is C23 plus g of j comma s minus j. So it becomes g of 3 and S has a single element 3 in it, minus 3 is null, right? So you remove the element 3 from the set, so it leaves you null. So the function now reduces to g of 3 null. So you get the cost of the edge C23 from the graph, from the adjacency matrix. 2, 3's value is 9 plus g of 3 null. You get it from the previous calculation to be 6. So 9 plus 6 is equal to 15. So similarly, you do it for g of 2, 4, you get a value 18. So the next time you do it for g of 3, 2, followed by g of 3, 4, then you calculate g of 4, 2, followed by g of 4, 3. So all these lie into a category where set S has exactly one vertex in it. So next what we do is we compute g of I comma s for set S which has two vertices in it. And please remember, I is not equal to 1. 1 does not belong to this set S, and I does not belong to S, right? So this formula is now g of ij. So i's value is 2, so 2 should not be a part of S in the first case. And j's value will be iterating. Once it will become 3 and the next time it shall be 4. So the equation now becomes minimum of Cij, so C23 plus g of j's value this time initially is 3, comma set S minus j, so removing of 3 you are left out with 4. So the equation now becomes g of 3 comma 4, comma, so again the next term now becomes c of ij, so I this time is still 2, j becomes 4, plus the next term is g of 4, 3. So the cost of the edge from 2 to 3 is 9 plus g of 3 comma 4, you get it from the previous step to be 20, so this entire term reduces to 29. And then C of 2, 4. 2 to 4 has a cost 10 plus G of 4 comma 3 has a cost 15. So 10 plus 15 is 25. So the minimum value between 29 and 25 is 25. So we select this. We select an edge from 2 to 4. So similarly, you calculate g of 3 comma 2, 4, g of 4 comma 2, 3. So please notice here set S has two elements in it. So after doing it, we get minimum value. We will have to select from all these three a minimum value. So we select the very first one, that is 25. So the next time S is equal to 3, so it means that S has all the three vertices and I is nothing but our source vertex. So G of 1 comma 2, 3, 4, again by the second equation will now have minimum of I is 1 for the first time, J's value will be 2. So C of 1, 2 plus g of j is 2, and removing 2 from the set you have 3, 4. So you will get the value of C of 1, 2 from the adjacency matrix to be 10 plus g of 2 comma 3, 4, you get it from the previous step, so its value tends to be 25. So similarly, the next term here will be C of ij. J's value now becomes equal to 3. So C of 1, 3 plus G of 3 comma, excluding 3 from the set, you have 2, 4. So C of 1, 3 from the adjacency matrix is 6 plus G of 3, 2, 4. You get it from the previous step and its value is 25. So 25 sorry, g of 3 comma 2 4, yes, it is 25. So 25 plus c of 1 3 is 15. C of 1 3 is 15. So 15 plus 25 becomes equal to 40. So similarly we calculate the other part also, and here we find the minimum value to be 35. So now we select a path from 4 to 1. So this is how we traverse from vertex. We obtain an optimal tour from vertex 1 to 2, 1 to 2, 2 to 4, and 4 to 3, from 3 back to 1.